Hello my dear students, welcome to my video on irrigation engineering, and today I will be delivering a lecture on dams and spillways. So please watch this video till the end. This video is the second part of the topic dams and spillways. I would like to request you all to watch the first part of dams and spillways topic, which was covered in my last video, before going through the second part. The first part of dams and spillways was about the external forces acting on a gravity dam, and it also covered several smaller topics. Wish you all a very happy studying. Today's first topic is elementary and practical profile of a gravity dam. First is elementary profile of a gravity dam. On the screen you can see the elementary profile of a gravity dam, which is also known as the theoretical profile of the gravity dam. When water is stored against any vertical face, then it exerts a pressure P which is perpendicular to the face of the dam, and this pressure P is acting at a distance of h/3 from the base. H is nothing but it is the height of the water which is stored in the dam. The pressure is 0 at the top and it is maximum at the bottom. You can see on this diagram. So a thickness required at the top is 0 and maximum thickness is required at the bottom. Thus a right angle triangle is formed, which you can see on the screen, with apex at the top, one face vertical and some base width. This face is vertical, which is the height, and the base width you can see on the diagram. Let h be the height of water stored and b be the width of the dam. So a right angle triangle with height h and base b is formed. For stability, the resultant force should remain within the middle third. So R is the resultant, which you can see it is on the middle third of the base. Now, two conditions should be satisfied to achieve the stability of the gravity dam. Let us now check what are these two conditions. First is when the reservoir is empty, and second when the reservoir is full. When the reservoir is empty, the external force P is 0 and its self weight, that is W, passes through the center of gravity of the triangle. So the point C is at a distance of b/3 from the hill. This is the hill part and this is the toe part of the dam. Point C is the extreme left end of the middle third of the base. Now we have to take moments about the point D. So this is the point D and the moment will be P into h/3 equal to W, that is the self weight, multiplied by b/3. W into b/3 equals to P into h/3. Now I will cancel 3 on both the sides. I will take B from LHS to RHS, and I will also transfer this P into LHS. So our equation will now look like W upon P equals to H upon B. We will now mark this equation as equation number 1. Now my dear students, we also know that P is nothing but the external force. This P equals to density of the water multiplied by square of the height divided by 2, and W. Now what is W? We all know that W is nothing but it is the self weight of the dam, is equals to density of the water multiplied by specific gravity of the material of the dam multiplied by base width multiplied by the height divided by 2. So we all know this two equations earlier. Now we will put the value of P here and the value of W here, and now our equation will look like W by P equals to WH square by 2 divided by W into rho into B into H divided by 2. I have done nothing but I have put the values of these two in equation number 1. Now cancelling the similar terms, we will get the equation will look like W upon P equals to rho B upon H. Now mark this equation as equation number 2. I hope this is very much clear to you. Now what we will do, we will equate both these equations because we can see W upon P is common. So after equating equation number 1 and equation number 2, we get H upon B equals to rho B upon H. H upon B, here you can see H upon B, so I have put it here, and rho B upon H, so I have put it here. Now we have to do cross multiplication, so H into H equals to B into rho into B. So our equation will now look like rho B square equals to H square. Now simply we have to take square root on either side of the equation. So our equation will look like B equals to H upon root over rho. I hope this is very much clear to you. This is very much important. Thus we can say that the elementary profile of a gravity dam is a right angle triangle with base width equals to H upon root over rho. Our next topic is practical profile of a gravity dam. I have drawn the elementary profile of a gravity dam with base width equals to H upon root over rho. In elementary profile, the maximum pool level or the FRL is at the apex of the dam. But in actual practice, water level can rise above this level due to various reasons such as heavy wind, waves or peak flood, etc. So, some safety margin should be provided at the top so that the excess water may not spill over the top of the dam. Again, some top width is also necessary for the stability and for providing the roadways over the dam. This safety margin is known as the freeboard. The amount of freeboard depends on peak flood, intensity of wind or height of waves. In normal practices, freeboard is generally kept from 2 meter to 3 meter. The top width of the gravity dam is denoted by A, and A is determined by Bly's empirical formula. A is equals to 0.552 root over H. Thus, the elementary profile of the gravity dam is modified by providing freeboard and some top width, and this modified profile is called as the practical profile of a gravity dam. Next is low dam and high dam. To decide whether a dam is a low dam or a high dam, first of all we will see a basic equation which is shown on the screen. H equals to F upon omega multiplied by rho plus 1. Here omega means the unit weight of water, that is 1000 kg per meter cube, and rho means the specific gravity of the materials of the dam, and F states the permissible compressive stress in masonry in kg per meter cube. Now on the basis of this formula, we will decide whether a dam is a high dam or whether it is a low dam. So if the value of H is greater than F upon omega multiplied by rho plus 1, then it is a high dam, and if the value of H is less than F upon omega multiplied by rho plus 1, it is called as a low dam. The following figure shows the section through a high level dam. In this case, the allowable stresses are often exceeded, and resultant of all the forces acting on the dam passes through the middle third of the same horizontal joint, for which the section of the dam is given an extra slope for achieving the stability of the dam. Now in this figure you can see the limit of the low level dam. This is the heel part of the dam and this is the toe part of the dam. Next topic is failures in gravity dam. Generally 4 types of failure are observed in a gravity dam. A gravity dam may fail in overturning of the dam about its toe, or by sliding or shear failure, or by compression or crushing, and by tension. Now let's have a detailed discussion on each one of these failures. Overturning failure of gravity dam. The solid gravity dam may fail by overturning at its toe when the total horizontal forces acting on the dam are greater than the total vertical forces, that is, its own self-weight. In such a case, the resultant force passes through a point outside the middle third of the base of the dam. The overturning may be caused at the downstream edge of any horizontal section. My dear students, practically such a condition does not arise at all, but a dam may fail much earlier by compression. Then you may be wondering, then what we can take precaution? Overturning failure of gravity dam. The solid gravity dam may fail by overturning about its toe when the total horizontal forces acting on the dam are greater than the total vertical forces, that is, overturning failure of a gravity dam. The solid gravity dam may fail by overturning at its toe when the total horizontal forces acting on the dam are greater than the total vertical forces, that is, its own self-weight. In such a case, the resultant force passes through a point outside the middle third of the base of the dam. The overturning may be caused at the downstream edge of any horizontal section. Practically, such a condition does not arise and the dam will fail much earlier by compression. Now, students, you may be wondering then what precaution we can take so as to avoid this failure. To avoid this overturning, resultant of all forces acting on the dam should remain always within the middle third of the base of the dam. This condition can be achieved in both the cases, when the reservoir is either full and if it's empty also. Next is sliding failure of gravity dam. The total horizontal forces acting on a dam tend to slide the entire dam at its base or along any horizontal section of the dam. The sliding may take place when the total horizontal forces acting on the dam are greater than the combined resistance offered by shearing resistance of the joint and the static friction. Factor of safety against sliding can be based on its frictional resistance as well as its shear strength of the dam. Now you can ask me that how we can take precaution to avoid this sliding. My answer will be sliding can be fully resisted when the condition for no sliding exists in the dam. What is that? We have to take tan theta equals to summation of all the horizontal forces divided by summation of all the vertical forces, and this tan theta should be less than the coefficient of friction of the materials of the dam. That is, tan theta should be less than mu. Mu is nothing but coefficient of friction of the materials of the dam. Compression or crushing failure in gravity dams. Due to excessive compression exceeding the permissible limit, the dam may fail. The excessive compression causes crushing of the dam materials or the safe bearing capacity of the soil. For the safety of the dam, it is necessary that the compressive stress of masonry should never exceed its permissible limit or safe bearing capacity of the soil under foundation. Tension failure or development of cracks in gravity dam. The tensile stresses should not be allowed to develop on the upstream face of the dam. But if due to some reasons tension is developed in the dam section, crack will form in the body of the dam and ultimately this will cause the failure of the dam. To avoid this kind of failure, we have to maintain the middle third rule. For high gravity dams, certain amount of tension is permitted under severest loading conditions in order to achieve economy in design. For this reason, tension up to 5 kg per centimeter square is permitted. This is done due to the fact that worst loading conditions occurred in gravity dam only momentarily, for very little times, and they never last or occur frequently. Next is galleries in gravity dam. Galleries are the horizontal or sloping openings which are provided in the body of the dam and are constructed longitudinally or transversely and are provided at various levels in the dam and interconnected with vertical shafts fitted with lifts or mechanical lifts. You may now be wondering that what is the use or function of providing a gallery in a dam? To collect the seepage water reaching inside the dam through the joints and pores of the dam. If this water is not removed, it will produce internal stresses leading to the failure of the dam. Galleries are provided to provide access to various internal parts of a dam. They are also provided to dissipate the heat generated during setting of concrete. They are used to plug the longitudinal joints after completion of the dam. They are used for drilling and grouting of the dam or the foundations. They are used to study the behavior of the dam after construction of the dam. They are also provided to feed various mechanical equipments inside it. They are used to operate sluice gate or outlet gates, etc. Galleries of various levels are connected by vertical shafts, and these shafts are generally provided with lifts and stairs both. Sometimes shafts are used to measure the deflection of the dam also. I have tried to explain this topic to you in a very simple and lucid manner. If you have learned anything from this video, please hit the like button. And also please share this video with your friend. And for more new updates, don't forget to subscribe to our YouTube channel. And don't forget to press the bell notification for instant updates. Thank you for watching this video.